Alright, this video is going to go over the second problem that you did in class, which was really just a lot of practice using the geometric model and the binomial model. So you already have the solutions and they're posted on the website. So I'm going to go through it fairly quickly here on this video, just pointing out a few things that maybe I haven't pointed out. The first few, we're looking at a geometric model because we're looking at the number of items until the first, I guess, defective item, and I guess that's the first success is finding the defective item. And so they follow the same pattern. The mean of a geometric is 1 over p. We never really derived that in class. It's derived in the book. We actually sort of did a parallel derivation to find the expected value of the winnings in that dice game. But the mean of a geometric random variable is 1 over p. Formula you should know, and it should actually make sense to you. Okay? Now, number 4, we're asked to find the probability that the inspector tests at least 30 flashlights before he finds a defective. So I'm writing the probability I'm finding. Now, what are the possible outcomes in at least 30? There's hella outcomes. There's an infinite amount, in fact. Okay, so we don't need to derive, or we don't need to use the sum of an infinite geometric series to find this answer. There actually is a formula in the calculator called the geometric CDF. Okay, and the geometric CDF will find the probability x is less than or equal to k when x is geometric. Okay, and so that's just the geometric CDF. The parameter of the model is p, and k is the thing we're finding less than or equal to. So if I'm finding greater than or equal to 30, I'm going to do 1 minus less than or equal to 29. I'm going to use that geometric CDF, which, by the way, where is that? That's under distribution, and it's right under the binomial one. There's geometric PDF. We don't need that because the formula for that makes so much sense. There's the geometric CDF. Okay, so you should use that. And that's how we got number 4. The rest of them deal with rolling 2 dice until we get a 5, adding them up to 5. Well, there's 4 ways that can happen. And so there's 36 total ways I can roll 2 dice. So that's 436. 1/9 is the probability we want. And we're just doing the same thing we did, but for a different geometric random variable. On the back, we're rolling the 2 dice a set number of times. So now this random variable becomes geometric. Okay, and we find those geometric probabilities the same way. The probability that we get at least 15 is 1 minus the probability we get less than or equal to 14. We use binom CDF. Notice here I'm defining a random variable, okay, and I'm saying it's binomial. Some of these problems, you've got geometric random variables, binomial, you've got normal. You want to keep them straight, so part of communication of your answer will be, defining that random variable and saying that it's binomial. The rest of the problem deals with, is a normal approximation appropriate? And appropriate maybe is not the right word, because in order to do number 8, we don't need a normal approximation. It's not necessary. This is the exact answer. But would it be reasonably accurate? Well, the rule of thumb again is that n times p is greater than 10 and n times 1 minus p is greater than 10. They both are. So it's not appropriate, but it would be not that bad. All right, so 10 and 11 asks us to find the mean and the standard deviation of that model, of that binomial model. And then 12 says use the normal model, and let's see how close we are. Okay, so I'm using this normal model. I'm finding the area that I want. I'm finding the z-score, and I actually get that it's about, according to the normal model, it's about an 11% chance. According to the binomial, it's about 14%. So they're not that far off, but they're also not that close. However, we could do what's called a continuity correction. Since we're finding the probability that x is greater than 15, greater than or equal to 15, there's some area under the normal curve that's between like 14 and 15. So what part of that are we included in 14 and what part are we including in 15? Well, there's no right answer. So let's just use 14 and a half and find that using the normal model. And what we find then is that we get an approximate answer that's awfully darn close to the actual theoretical probability. So that's called the continuity correction. You're not really responsible for that on a test, but just realize that that's a way that we can make our normal approximation even more accurate than it is.